All right, today our focus is on few things. Here is tackled Laplace transforms of special functions. Basically, what we're talking about here, we're talking about simple things like unit step function and the impulse function and so on, and how they interact with other functions in terms of Laplace transform. So what I'm going to do here, I'm going to use the definition to derive the Laplace transform of these functions. So let's get on it. Here is the unit step function, given the unit step function, which is ut, 0 before when t is less than 0, and the 1 all the way from t equal to 0 onwards. And of course, according to our definition of Laplace transform, you would say the Laplace transform of this is the function from 0 to infinity, the integral of that function, ut, multiplied by e to the power minus st dt. That's the definition. Then, I think it's clear that this integration starts at 0, when already ut is what? 1. And it turns out that we are basically calculating the Laplace transform of the constant function 1, which will end up being this. And if we compute this, we'll do exactly what we did before. That will be limit as t is approaching infinity of the integral from 0 to t of e to the power minus st dt. And integrating that, we know that this integral is going to be minus e to the power st over s and we know that here what we're doing, we're calculating the limit of this as t is approaching infinity, and this here we evaluate like a definite integral from 0 to t. That's what we get there. So this becomes equals to the limit as t is approaching infinity, e to the power minus st minus e to the power 0. That's what we're calculating there, the limit we're calculating. Are we clear? Are we so far there? Fine. This is exactly something we did when we were doing for 1, so there's no real difference, but there's something I want to show you which is going to come up a bit more interesting than this. So this is 1 minus 1 is 1, and as t is approaching infinity, this exponential decay will approach 0, hence it's going to be negligible. So what is left here is simply 1 over s. So you can see this is exactly the Laplace transform of the constant function. Are we together? Okay, so let's look at the version, another version of this unit step function. In this case, I'm talking about the delayed version of the unit step function. Just notice here that we've got a new signal, which is x, coming from delaying, which is originates from delaying the unit step function by 2 steps. So in our delay here is 2. And then what we're going to do here is exactly the same thing. Say the Laplace transform of x of t is the integral from 0 to infinity of x of t e to the power minus st dt. Now check what's going to happen here. This integral starts from 0 to infinity. So if we now to take it according to the limit and say is the limit as t is approaching infinity, integral from 0 to t of x of t e to the power minus st dt. Notice that this function is defined piecewise. It says here, the unit step function defined like this. It simply says it's 0 before 2 and it's 1 from 2 onwards. Is that clear? Yeah. Okay. So then what we have to do here now, we've got to integrate from 0 to 2. What are we integrating there? We're integrating 0 times e minus st dt. And we don't even need a limit here. We don't need a limit. You need limit here. We're going to say plus the limit as t is going to infinity of the integral from 2 to t. I hope you understand what I'm doing there, isn't it? And then here, this will be 1 times e to the power minus st dt. And then obviously this is going to be equals to 0. And then when we integrate there, you remain with something like this. Limit as t is going to infinity that is over s there. What are we having there? Let me first fill up this plate here. I was too fast there. What we have here, we have limit as t is going to infinity of this minus e to the power minus st all over s evaluated from 2 to t. Is that clear? So when you come here now, what we're going to do, we're going to say minus e to the power minus s capital letter T minus e to the power minus 2s. If you understand what I'm doing there. Is that correct? Okay. Then again, this part will again decay to 0. And then we're left with that. Then the answer here becomes simple e to the power minus 2s all over s. So what is that? That is the Laplace transform of a delayed unit step function. You must see that the delay comes here as a coefficient of s. I said that the delay is 2, and you see that that delay there, it comes there as a coefficient of s, and that is Laplace transform. Am I making sense? Okay. So simply what I'm trying to say that if now you get in an equation, maybe you could go on the right hand side wherever you get an equation, the right hand side being a delayed unit step function. This is what we're going to put in place if you need a Laplace transform. Is that fine? Okay. Let's go on now and come to the impulse function. There is the impulse function. We want to find the Laplace transform. This one is a bit challenging because we need something which maybe some of us are not aware of, and that is called the shifting integral. You just go to the books and see something called, I think it's called shifting integral. The shifting integral basically says this. It's an integration, let's say, basically from minus infinity to infinity. And this integral, what it does is integrates the product of f multiplied by delta. So what happens here? This shifting integral, if you really remember what happens here, the delta function here the delta function here, I could have represented it as delta t minus 0. Agree or disagree? But I will try to convince you that it's the same thing. What I've written here is delta t is equal to this, the same thing as saying delta t delayed by 0. Is it the same thing? Okay. So then you notice that this function is 0 everywhere where t is not equal to 0. In other words, where the argument is not equal to 0, it is 0. Exactly when the argument is equal to 0, it shoots out a value 1. Is that right? So if you take that kind of understanding and come to this one, you would basically say this function, delta, will only react when its argument t minus a is equal to 0. And that means exactly that t at that time will be equal to a. Are you saying 1? I think it's a. Where did you get 1 here? Come again? A, yes. So then, if you were to get this kind of integral, what would you do? This function will be 0 everywhere except at a. At that time a, this function will be realizing 1, and this function will be also seeing a value of what? That function, the only value where that function, this function will consider now, it will consider as f of a. But what is an integral? An integral is essentially a sum, a continuous sum. But now this sum is continuously adding zeros, and suddenly it has gotten to add a value of f of a times t. So this integral is simple f of a. That's what the shifting integral is. I know you didn't do this thing at Math 3 or whatever, but it's something, if you understand integral very well, it's something you can understand. This type of things fall in another big chapter of integration called improper integration, which normally we don't do at this place. But we need it if we were to understand what is the Laplace transform of this. So I'm going to use this shifting integral. I hope the spelling is correct here, but if it's not correct, they will pardon me, those who wish to pardon me. Those who don't want, they may not pardon me, but English is just something else altogether. Okay. So let's come now and develop see what's the integral of delta what? T. So what we're going to do, we're going to say Laplace transform of delta t equals to integral from 0 to infinity, of course, of what? Of delta t multiplied by e to the power minus st dt. I really don't need to do a lot of things here. What I can do, this integral is exactly the same as the integral from minus infinity to infinity. Whether I consider it this way or this way, it's exactly the same thing. Why do I want to consider it this way? Because I want to adjust to this language which is spoken here. Do you understand my logic? Yeah, I want to adjust to this language which is spoken here. But it really does not make a difference. So then what's happened here? I will write here delta t minus 0, like I said there, multiplied by e to the power minus st dt. I've just taken this thing here and basically translated it and wrote it in the language of the shifting integral. Because I can take advantage of this, that this thing here as it is the same as that. And then here in this integral, my a is identically equals to 0. So according to the shifting integral here, the answer to this is simply e to the power minus s evaluated where? At 0. Like f here was evaluated where? At a. Understood? Then this is 1. And that's what exactly the Laplace transform of the impulse function is. It is a constant 1. So I hope now you understand that tomorrow, if I give you that the signal I'm talking about here, he has got a Laplace transform x of s, and then say this transform is 1. Then you must understand that if I want to go back to the time function, I must simply say x of t is equals to delta t. I hope you understand, but if you don't understand, I'm here. You can talk to me. I can communicate relatively well in the language of the Queen. Are we there? No questions? Right. I think at this point, if you understand this too, the only thing which is left now is to look at examples, which I don't want to look at them now because I need to do something before we get this thing. But you've got notes to take this thing. We'll refer to this as we move forward. Is that all right? So at this point, thank you for listening. My name is Charles Waswani Msipa.